Hello, and welcome to today's webinar with IOP ebook author David Elliott. David will be reviewing the current state of play in the renewables field, technologies, costs, storage, grids and future potential, and asks, can renewables deliver? During the webinar, we welcome your questions, so please use the question and answer facility to send them in at any time during the talk. David will then try and answer as many as he can at the end of the presentation, and we will respond to any unanswered questions by email once the webinar is over. On that note, I'll hand over to you, David.
Thanks. I've reviewed the renewable energy options in an IOP ebook, and I'll be summarising them here, sampling some examples at least. It all reflects the work I did over the years at the university and my subsequent post-retirement activities. In particular, it's based on a blog I do, Renew Your Energy, for the Institute of Physics Environmental Research web. So I thought, having done this regular weekly blog, an e-book run by the IOP would be a good follow-up, fast and accessible. That seems to be how it's worked, and certainly I wanted to pass on the sense of enthusiasm and excitement that's apparent in this field. And I think the number of downloads I've had of the book, I seem to have succeeded. So why is it lots of people are thinking that we should go for renewables? That's the core argument. The first, most obvious thing is that we can't carry on using fossil fuels forever. The reserves are finite, going to run out eventually, and using them anyway damages the climate. We can't actually use them all up. See a temperature increase graph. There are plenty of renewables. The planet actually receives much more solar energy than it could ever use. We can find ways to convert it into useful energy, of course. More in each year coming in than all the finite fossil fuel reserves put together, and nuclear reserves as well. So, as you can see from the chart, we can get this input continuously available at no direct cost into the distant future. Clearly, the actual resources are very large for the various subcategories of renewables, but we have to learn how to convert each one into a useful form of energy, economically and reliably. We're doing quite well on that. The progress has been quite surprising in some areas, like tidal and wave, perhaps not the most obvious, but wind and PV solar there, the blue and the green, both accelerating. Interestingly more so than nuclear, the red one. And at the same time, costs are falling. Here's another chart showing the quite surprising fall in PV costs, the red line, and similar but less dramatic costs for wind, compared again to increased costs for nuclear. There's another set of reasons why you might want to support renewables, and that's to do with the embedded energy costs, or the energy used in making the energy. The energy needed for renewable energy conversion systems is relatively low. In most cases there's no fuel energy cost, it's fuel's free, and the fuel processing cost is negligible or none. The only cost in energy in terms is the construction of the system. And that, of course, compares strongly with all the other technologies where there's a high fuel cost, but in the case of nuclear, there's quite a high fuel production cost. As high-grade uranium becomes scarce, that will increase. There are lots of studies showing that if we wanted to, we could get up to 100% of our electricity from renewables by 2050. That's within the EU or globally, at reasonable cost too. Some say we could also get to near 100% for all our energy, not just electricity. That's heat, transport fuels as well as electricity. The last time I counted, there were about 65 studies like this, covering the UK, US, EU and the world, all saying 100% by 2050 is possible, technically. The other case for renewables is that they're popular, more so than the other options. It's not really surprising, given that renewables do not have the health or safety risk associated with using fossil or nuclear fuels. Their environmental impact is also going to be very low. The impact it does have is can be local and small, not global and large. So what exactly have we got on offer? Looking at power first, electromechanical power. It's how we started out with renewables. We used wind and small tidal mills to grind corn. Now we've learned how to use those technologies and hydro as well to generate electricity using fluid flows of various sorts. Hydro, of course, was the first and still the biggest renewable around. It's widely used. About 50 countries get over half their electricity from hydro, some of them up to 100%. Many of the 860 odd gigawatts of hydro capacity is quite large, of course, multi-gigawatt projects, but about 10% of that is a few megawatts each, little plants. They're much less invasive, and in general there's an argument that large hydro is going to be less attractive in the future than small hydro. The other new option, of course, is wind. That's the biggest of the new renewable energy technologies. Expanding quite dramatically. We're up to 320 gigawatts or more now in place, with China clearly in the lead, followed by the USA and Germany. It's also expanding in the UK and also offshore. The UK is actually in the lead offshore. We have 6 gigawatts of offshore in Europe, and about half of that is from the UK. So interesting developments, new technology. The UK's offshore wind resource is actually vast, because it's not just wind, there's also offshore wave and tidal resource, and this chart shows some of the numbers. We're talking about 6 times more electricity than the UK needs. And that's assuming we can use floating systems. The picture on the right shows a offshore floating wind turbine. The advantage of that, of course, means you can go offshore into the very deep water, not just in the Dogger Bank and the shallow areas off the east coast. Once you start doing that, Britain becomes much bigger. So that red line around the outside of the map there shows the new area of our energy take. We've effectively made Britain even greater. And of course, it's not just the UK. This chart suggests that globally, if we wanted to, we could generate nearly all the world's electricity requirements from offshore wind. No one's suggesting we're going to do that. There are plenty of other sources as well, but it's interesting to get a scale on the whole potential. Not as big as wind. Wave energy is one of the other ones. We have sites around the world. There are some problems with wave. It's again specific, very much location. Not as big as wind, but one thing about waves is that the wave persists some hours after the wind has blown across water. That's how you get waves. So in a way, wave energy is a form of stored wind power. The global resource for tidal is not as big as wave, but it's still quite large. And again, very site-specific sites, as you see in Europe. But the attraction of tidal is it's very predictable. We tied to the lunar cycles, which we know very precisely. Big barrages, in fact, hydro dams built across estuaries, can be invasive and probably quite expensive. Smaller underwater wind turbines, as it is, small tidal current turbines seem like a much more appealing and less invasive technology. I think that's what's going to go ahead. The tidal field, but what about wave versus tidal? Which of those options are going to win? There's some interesting differences, like wave energy is complicated. You're dealing with an interface between sea and air with complicated multi-directional energy flows, constantly changing, very unstable, very hard to extract energy. By comparison, you go 20 or 30 feet down underwater, everything goes smooth and laminar. You can have a storm up the top, but nothing underneath. So tidal flow is going to be much easier to use as an energy source. So I suspect tidal power is always going to be easier and cheaper to develop. But there are both technologies being developed in the UK at the moment, and it's an amazing flurry of innovation in this country and some others. UK's in the lead, and we might get around 20% of our electricity from these sources eventually. Meanwhile, there's completely different areas, heat. Green heat options. Of course, we've already historically used biomass for heating, wood and other forms of biomass. That's the first thing we ever did in terms of renewable energy, but we didn't do it very sustainably. Burnt off forest and the rest rather quickly. We've got better at that now. We can know a little bit more about how to use biomass. We're also using solar, and we're also using geothermal heat. So let's have a look at biomass. As you can see, biomass is a big source. We've got physically large potentials, but and of course it can be carbon neutral if the rate of regrowing of biomass, which sucks in CO2 from the atmosphere, is the same as the rate of use. It's roughly carbon neutral. There's some disagreements about the detail. There may be some delays before the CO2 is reabsorbed, for example, and you've got to subtract the energy costs of transport and processing and other things. So it's never going to be exactly carbon neutral, but it is certainly a renewable option available to us, and there are a whole different range of biomass sources, residues from farming, agricultural, forestry, industry, municipal waste, and food waste as well, things like that, all add up into reasonable percentages. The only problem, one of the main problems at least with biomass, of course, is it takes a lot of land. That's not surprising. You're using solar energy through photosynthesis of plant material to make a burnable or combustible or rottable material, and photosynthesis is very inefficient. So inevitably you're going to need very large areas of biomass to grow enough fuel for electricity generation or from vehicle fuel. You need a lot of land, and much more than any other option, as that chart shows. Not a problem of land, because we're actually going underneath it is geothermal energy, deep heat from underground for heat production, not directly, but also for electricity generating. There's about 11 gigawatts of geothermal generation at the moment, and it's expanding quite rapidly. That's one of the bigger future areas we can expect to see as interest in renewables expands. It's not strictly renewable in the sense that the heat gradient, when you're extracting heat from any particular area, that heat gradient will fall. So you, after a few decades at least, you have to move on to a new site. But the heat gradient will just re-establish itself again. So it's sort of renewable in the longer term. And of course, the actual energy source, heat, is from radioactive decay deep in the earth. So in fact, it's natural nuclear energy. Whether everyone's going to see it that way is another question. Really natural is solar energy. We have a huge resource of solar energy, and maybe not everywhere we want, personally, but the scale is large and fairly widespread. We also have a lot of it being used already. It's quite interesting that the solar heat usage in forms of solar heat collectors on buildings and so on is now nearly as much in gigawatt thermal terms, 150 gigawatts, as wind. So wind gets a lot more promotion and people know about that. Solar thermal is actually off the same board and expanding around the world. One thing you can do with it, of course, and what you have to do if you're trying to use it in some countries, is store it. Now, storage might sound difficult, but it can be done. Here's a large solar thermal array in Denmark with an interseasonal heat store. This is a large underground cavern full of water. Hot water is heated up during the summer from solar heat and used to provide heating in the winter. Interseasonal heat stores. For northern countries, Scandinavia and so on, is now catching on. Surprisingly, it's even catching on in really cold places like Canada, where here's a large series of houses with an interseasonal heat store underneath. This can get pretty cold in Canada. On the other extreme, we've got sunnier climates. We've got direct, bright sun. You can use solar heat to generate electricity. concentrating solar power plants, sometimes they're called concentrated solar power plants, CSP. Using focused sunlight, that raises steam or some other fluid to run a turbine generator, but some of that heat can be topped off and stored in a molten salt heat store, and then we release this heat again to raise more steam so that you can run the turbines 24/7 round the clock just from this whole plant can just supply continuous power. There are quite a few of those now being established in North Africa, originally in the US and Spain, but now across North Africa. The Saudis, for example, are planning 25 gigawatts of CSP. It's not actually competitive with conventional sources, but if you've got the land and the sun, and it's an interesting option. You see here, North Africa is scaled up with various CSP projects scattered around on bits of Middle East. Those red squares indicate the areas you need to supply the top one, the whole of the planet with electricity from an area of CSP. The second one down, just the area needed to supply the whole of Europe. No one's suggesting you can do that or we want to do that, but it does indicate the scale of the resource and the vast desert areas we have. That was heat. The other component of what comes out of the sun, of course, is light, and that can be used directly to convert the light energy into electricity. Direct conversion by photovoltaic and photoelectric cells is an attractive option because there's no moving parts, silent, you can mass produce them, and they're getting cheaper. They started off quite expensive, but it's getting rapidly cheaper. So much so that it's moving ahead faster than from a low start when all the renewables others. The rate of growth is ridiculously large. Here we have there's a period up to 2011, but now I think the current figure is 120 gigawatts of solar around the world, with even the damp, cold, not so hot, sunny the UK has got nearly coming up to 3 gigawatts, which is quite surprising. As you can see, the options are to put them on rooftops, and Germany has been the one that's been making the most progress, 32 gigawatts in Germany, with individual consumers buying their own system under the feed-in tariff, accelerated dramatically in the last few years. The largest project in the world so far is a 600 megawatt project in India, but around the world PV is moving ahead, and the technology itself is accelerating with efficiency levels dropping up. Here's a picture of some of the advances in new cell technology with efficiencies up to 44% or more. The point about efficiency, though, is that the way to get really high increased efficiency is to concentrate sunlight. It's cheaper to build mirrors than it is to build solar cells, so mirrors and focusing devices of various sorts for lenses are going to be able to push the efficiency up to 80%, and tracking the sun with rotating mirror machines like the ones in the picture also helps. It's sort of concentrated solar power, concentrated PV, CPV, it's catching on too. Probably competitive with concentrated solar power thermal version that I talked about earlier. So we've got lots of options. I've only dealt with some of them. How do we actually put them together? PV, wind, wave, tidal, and all the rest. Some of them are variable. Some need backup when there's no wind. Some of that can be from other green sources like hydro, geothermal, biomass, storable biomass. Some of it from storage of excess from the wind, wave, tidal. There are options for that balancing renewables like that. But there are other things you can do. You can also balance demand. You can reduce demand using smart grids, and you can also swap power around between countries using super grids. So we can take a look at that now. The super grid, of course, allows you to meet peak demand by shifting power from countries where there is some to a country that hasn't got any at that particular time. But there's a smaller and localized version of that is to use smart grids. What you do, as the picture shows, is to delay some peaks. The orange area at the top is shifted basically onto the saddle onto the side of that curve there, so the peak falls later, and there's a time when you can meet it more easily. One way to do that is by having variable pricing of electricity. If consumers are faced with a large charge during peak demand times, they may prefer not to run some devices until it goes down a bit in price. So that way you get an automatable system that can be done. It doesn't have to be each individual consumer making decisions every second. They can pre-program to a price device to tell them, well, I'm never going to pay more than X% extra, so it'll pre-program my fridge freezer to go off for an hour, for a day, because I don't particularly want to pay too much for it, and it can be happy to do that. There are smart demand management techniques which can deal with some of the peaks. There's also a range of storage techniques. Of course, hydro storage is the currently mostly used, where you pump water uphill behind a hydro dam, let the water back out when there's a need for the electricity. There's a range of other storage devices. So storage generally is quite expensive, so switching demand around may be a cheaper option. But the simple point is we've got an awful lot of power on the grid when we've got a lot of renewables, because we tend to have to oversize to make sure we've got enough power. There'll be times when there's too much. So the problem is excess power, not enough. And of course that's where the supergrid really comes in, because then you can start shunting it around. If you have not just wind, but wind, solar, geothermal, all in various parts of the country, northern hydro, northern geothermal, wind in the North Atlantic and the North Sea, and then biomass in Central Europe, and solar in North Africa, all firing off at slightly different times. We can rebalance the whole thing with a supergrid network around Europe, as this picture shows. It would be interesting to see if this is developing. Some bits are already in place, some bits are developing. The debate is going on at the moment. There's another approach, though, being promoted by Germany particularly at the moment. If you've got a lot of excess electricity from wind some of the time, well, you can convert it into hydrogen by electrolysis. And once you've got hydrogen, then you can do all sorts of things with it. You can use it as a fuel later when there's a need for the electricity, when wind power is low, say. Or you can run it into cars. You can use it as a vehicle's petrol substitute, like LPG, SNG. Or you can convert it into methane with a bit of carbon dioxide pulled out from the air from the power station exhaust, and do the chemistry and convert it into methanized methane, and then store the methane. All of which means it gives you a lot of flexibility. This so-called power to gas, or sometimes wind to gas idea, is being pushed in Germany as a long-term possibility for balancing their grid system. Okay, so there's a lot of technical options. How's the race going on to develop them? Here's the global wind race with Germany, US, China in the lead. It's interesting to look at how rapidly wind is moving ahead in China, for example. You see the blue line. PV not so rapidly, they've only just got started with that. Nuclear there is still expanding, but this was before Fukushima, and after that they slowed a little bit. So pretty clear that wind is leading in China. If we go to US, well, back in 2008 was when wind started getting cheaper than the other options, and wind is to double renewable outside hydro in US. And of course in Germany it has this plan for going to 80% renewable by 2050, with, as you see there, blue and yellow, wind and PV accelerating up rapidly. Come to the UK, situation is not quite as attractive, unfortunately. The UK is at the bottom of that league table there on the right. If you look, we just managed to beat Luxembourg and Malta, which is a little bit embarrassing. This is a little bit odd, since the UK has got the best wind, wave, tidal resources in the whole of the EU by far. Scotland, for example, has got likely to be 100% renewable if it goes independent. So what's happening? Various explanations, but I think one of them is that the targets we've set have been fairly ambitious, and they're going to get even less ambitious after 2020 there are no targets for renewables. It's more or less that's it. And this is a government projection, DEC projection of what might happen in that situation. Gradual decline in the rate of renewables development. It falls off. At the same time, we're getting messages from DEC that they really want to go even more into nuclear. We've got a nuclear program already, but talking about 75 gigawatts, 86% of UK electricity from nuclear possibly by 2050. Not actually a plan, but it's the sort of thing that's being talked about. Maybe an explanation of why renewables are not being pushed as much as they are anywhere else, most other places in the world. Not everyone agrees with that. There's E.ON, the German company, pulled out of the UK nuclear program, saying that felt the UK would be better served by renewables and energy efficiency. So the situation in the UK is a little difficult to explain. A Hinkley nuclear power plant looks like it might start up at 2023, assuming it goes ahead, at which point it seems like wind, on land wind certainly, and PV solar are going to be cheaper. So it'd be odd to have a stranded asset of a nuclear plant, a brand new one, which is going to be less commercially attractive than other technologies around it, even then. I find it difficult to explain. To try and make sense of the situation, I worked with a Pugwash group and produced a scenario using the DEC, the 2050 calculator system, which is available on the web. Put in all the data and go for 80% renewables, fed in all the information, and here's what the result came out after a year or so. Quite hard work. The scenario we came up with balanced supply and demand quite happily. We managed to avoid having to import any biomass at all, so we were using indigenous biomass only. Even when the renewables were very low, the variable renewables like wind and solar, we still managed to get supply and demand meeting each other, and actually with no need for fossil backup. We managed to back up the whole system without having extra standby fossil backup plants. There's still some fossil in the system because it's 80% target. But the whole system comes out slightly cheaper than a Pugwash high nuclear scenario that was done at the same time by other people, and the renewable scenario actually cut emissions a bit more. And most interestingly, it also led to quite large export because of the large wind component. We had at times large amounts of excess surplus wind, and that would earn us selling it abroad 15 billion a year, which would at least pay for the supergrid links and a lot more. And finally, if we used some of that excess wind to make gas, hydrogen, methane, we could use that as a backup option, which means we could take the whole system to 100% renewable with no fossil, no nuclear, no nothing. Here's a picture of scenarios that came out. You see above the black line there is the excess power that could be either exported or used to make gas to balance, to move the whole thing to 100%. The other authorities have made similarly positive statements. Here's World Energy Council, not 100%, but at least saying up to 48% from renewables of electricity by 2050, much higher than the nuclear estimate is. Let's see, we're talking about up the maximum 11% from nuclear. So it's interesting to see the World Energy Council, a conservative organisation, talking up renewables strongly. International Energy Agency, an even more conservative body, saying wind, waves, all the rest moving up to, massive rate of growth, 40%, up to, say, 25% quarter of global electricity by 2018. So it's a significant expansion. The IEA's executive director making the point that some of the new renewables are now getting to the point where they no longer need major economic incentives. The subsidies have can gradually be withdrawn. You'd expect subsidies for a while for new technologies, but that it's within the sight of some of them not doing any at all. And finally, we've got the IEA saying that the extra cost of balancing to deal with the variability might initially cost a bit, 10-15%, but they suspect that as the increasing reduction in prices occur for renewables, of course you have to remember there's no fuel prices, so you're competing against technologies which have got increasing fuel prices all the time. If the cost of CO2 as well is added, some sort of energy tax, then the renewables extra cost is more or less zero. We're talking about a system that is no more costly than what we've got at present. On that sort of basis, well, we can see this sort of chart. If you assume demand is going to carry on going up like the black line, 2% a year, if you want to get rid of fossil fuel and nuclear, the finite fuels, coal, oil, gas, nuclear, uranium, the red line going down to zero by 2050, well, renewables have to accelerate up like that green line, and that turns out, if you do the arithmetic, to be 5.2% per annum increase. Now that's not particularly dramatic. Some countries can't do that, but at the moment we've had countries doing 20s and 30s and 40% increases. It doesn't seem impossible for the get up to 100% renewables by 2050. On that basis, I produced this new book which argues that case, and I've also got a whole series of websites, you can see blogs and such like up there. I hope you find them useful.
Thank you, David, for that very interesting presentation. Now, we've had a couple of questions come in. So the first one we've got here. What are the major obstacles to the expansion of renewables?
Well, I'd have to say the most obvious obstacle is delaying the transition is nuclear power. The commitment to nuclear around the world seems to divert resources away from the renewables program. You spend money on nuclear, not spending it on renewables. There's also a mindset of high technology of one particular sort versus high technology of another sort. I think we need a vision to look at the new approach, which is different, involves some change, and change is always painful, and the status quo will resist. But I can't see an alternative. We have to eventually replace all our fossil, nuclear and other conventional fuels as they run out. So we have to go renewables at some point. It's just a matter of when.
Thank you. Another question here. Someone asks, which renewable will win?
Well, hydro and traditional biomass, of course, are the largest at present, so they've already won historically. But of the new ones, wind is the obvious winner by far, and on the offshore. But some say PV solar is going to take over a longer term, and certainly the resource is very large, and the cost of falling dramatically. So it could well be that PV solar takes over in a decade or so. The others, like wave and tidal, geothermal, things like that, they're going to be smaller probably. The modern biomass expanding significantly, and there's a whole lot of debates about land use, of course, which might constrain that. So hard to say. I'd put certainly wind at the moment.
Okay, I've got one question just come in. It says, I read this week that Siemens plan to invest 310 million in the UK wind turbine factories. Your presentation shows that the potential for wind energy in the UK is large, so this would suggest it is a smart investment. However, I also read a lot of negative press querying the long-term future of wind energy. Why does it get negative press, and do you feel wind energy has a strong long-term future as a source of energy in the UK?
Yes, it is very good news that Hull's to get 1,000 jobs from a wind turbine manufacturing plant being built by a German company. It's interesting. Germany sees the UK as a good investment target for renewables and not for nuclear. Why is it a bad press? Well, the English are proud and defensive about their landscape. That's what makes us English to some extent. And there have been some reactions to visual intrusion from wind turbines, which is the media loves conflicts of this sort. There's a bit of a problem. The funding system used in the UK, the renewables obligation, tends to push companies to be profitable, and to do that they tended to have to invade windy sites. And I think to some extent we got this backlash due to the nature of the renewables obligation and the impetus it had to invade uphill, often sensitive sites. That didn't happen in Germany. I mean, didn't happen in Denmark. Most of the projects in Germany are in sites that couldn't be used in England because they're not windy enough. So there's partly an own goal. The backlash against wind has certainly produced a sort of a slight aura of discontent and concern. That's, I think, an unfortunate thing, and it's not common elsewhere.
Okay, thank you. One other question here. What is solar hydrogen energy, and what are its prospects as a variable energy source?
What is solar hydrogen? Well, any form of renewable electricity, say, can be converted to hydrogen. You just use electricity by electrolysis to make hydrogen gas. So that could be solar electricity or wind electricity or whatever. But you can have direct hydrogen conversion from solar at high temperatures, focused solar, very high temperature, big mirrors and domes, focusing temperatures to get up to many thousands of degrees, and you can dissociate water directly, not by electrolysis. Not very efficient. But there are technologies being developed for the direct conversion of solar into hydrogen, so that would be an option.
I've got a question here about policy. How and why does renewable policy differ around the world?
You'd think rationally that the countries with the best renewables resources would be the ones pushing it the most, and that's because the UK has got the best renewable resources of anywhere, pretty much, per capita. China has a very big nuclear program. Well, a reasonably large nuclear program. I mean, perhaps 2% of their electricity coming from electricity in China, whereas their renewables program is much, much bigger. That's because they have a particular vision of going for renewables. Same for Germany. Germany's wind resource is terrible. As I say, we would not think of building British wind farms in Germany would make any money, but the Germans have gone for it because they want to. There's a vision there. So a lot of it is to do with political vision. It doesn't map onto any easy left-right perspective. Germany's not particularly leftist country, and the UK is not particularly, well, you can decide for yourself at least. I think some of it is accidental due to countries' histories. There's no easy explanation, except around the world, those countries that are pushing for nuclear, which are not very many, are the ones that aren't really supporting renewables, and the ones that are pushing for renewables aren't supporting nuclear. So there's a division there. So now you need to decide why are some people nuclear and some people not nuclear. Maybe that's the crux of it.
Okay. Got a couple more then. Which technology for renewable energy do you think is the most promising? I think here, which technology for renewable energy?
It's just promising long term. I'm very keen on the wind to gas idea I mentioned, the idea of converting surplus electricity from wind, solar, whatever, into hydrogen gas and then storing it and then using that for balancing the low arrival of wind at other times. So that is a sort of game changer technology, to misuse that phrase again. It's really actually not a bad word. It would change the game completely because it solves the intermittency problem at a stroke. Given that the electricity you would be using would be thrown away otherwise, the economics are not going to be too difficult.
Right. I think we've got one last question, which is quite a good one to wrap up on, I think. In an ideal world, what would you like to see happen in 20 years' time?
20 years' time takes us up to 2030, 40, something. I won't be here for one thing. I would like to see renewables up to a healthy 30–40% around most of the world. That looks like being the case for lots of Europe, bits of Latin America, lots of Asia. So I think by then we will have come to a resolution of the issues about climate change. Are we really serious about this or not? Come to some sort of decision about nuclear. Are we really going to try and keep going down this route, which we've had so many problems with? I always thought it would be nice to think things were a little clearer and that we'd be facing much more interesting problems, which is what I face all the time. The technical problems of renewables, those are the interesting challenges in scientific and technological terms. rather bored with the debates we have, particularly in the UK. Back at the starting gate, oh, shall we go this way, shall we go that way? Let's get on with one thing or another and get stuck in. There's some really difficult issues to be resolved about some of the renewables. I mean, they're not all easy. We need to get stuck in to the technology. That's the fun, and I hope people will be in the middle of that at that time. Yeah.
Okay, thank you very much. Unfortunately, that's all we've got time for today. If your question hasn't been answered, we'll email you a response shortly. Also, please feel free to rate the webinar using the ratings button on the top of the presentation screen. I'd like to thank David for a fascinating presentation, and thank you all for joining us and listening and everybody taking part. I hope you found the webinar useful and of interest. So please do tell your colleagues about the webinar. It will be available to listen to on demand within the next 24 hours. You'll be able to find the link on the Renewables book About the Author page on iopscience.org. This webinar is now over. Thank you and goodbye.
Dear friend of mine, Joe Abbas,